Welcome everyone. It's a bit of an unusual experience for me to be standing in an early evening talk slot. It feels a bit like an after dinner speech, but thanks to John and the organisers for inviting me. In truth, it was actually a bit more like arm twisting, I think, to get me to give this talk today, but I'm happy to do it. I'm delighted to be here, and great venue here in the Joel Sock in central London. So thanks to the organisers for inviting me and the Joel Sock for putting on this event. And as John says, there's a really great lineup of speakers over the next couple of days, and I think it should be a really, really interesting, nicely focused meeting. And I'll be doing a sort of bit of a basic warm-up to get you in the mood, really, rather than trying to present too much complicated science at this stage of proceedings. So, some of the things I'll be talking about, some of the research elements I'll be presenting are not my own work. They're a work of a group of people that we have based at the Natural History Museum and the Load Research Group. So I'd like to acknowledge all of those people, postdocs and PhD students who've been involved in our work in porphyry systems over the past number of years. And some of those, some elements of those students and postdocs' work will appear during the course of the talk, and I'll try not to steal too much of the thunder of the postdocs who'll be presenting later in the conference by stealing their best ideas and presenting them as my own. We're also grateful to the team in the Natural History Museum in the Imaging and Analysis Centre who run the instruments there, a world-class facility, without which we wouldn't be able to do all of the things that we can do. But my work and a lot of the ongoing collaboration was with the group at Codes at the University of Tasmania. So some of the things I'll talk about, particularly on the exploration targeting side, we're really working on and developing in our own ways as a result of collaborations that were initiated with the University of Tasmania when I spent a sort of 2-year extended sabbatical there back in 2008. We're also grateful to the sponsors of the Load Lab. So the Load Lab is a facility within the museum that's fully funded by 3 companies, Quantum Pacific Exploration, Junior Explorer, Anglo American and Rio Tinto, and we're grateful for their support for our research activities. So the talk outline is pretty straightforward, really, a bit of an introduction to ore deposits to get us all on the same page, geological characteristics, and some comments on the controls of ore formation. So really it's a bit of porphyry geology 101. So any of the porphyry aficionados in the room, feel free to go to sleep, and just maybe, if you're not asleep, maybe just enjoy some of the rock photos I've liberally spread through the talk. But then I'll go into a bit more detail, give some examples at least of whole rock and igneous mineral chemistry indicators that we might be able to use to assess the potential fertility of a magmatic system, whether it was capable potentially of forming a porphyry ore deposit or not. And then I'll talk about some of the tools we've been developing for exploration targeting. So rather than just trying to assess whether something might be there, when you know you've got a hydrothermal system there, but you're trying to work out where the center of it is, and potentially how well endowed it might be, even if it's buried, so even if there's not much information at the surface to help you. So they're the topics of the talk today. So we start off, is it possible to dim the lights a little bit more, perhaps? Possible to do that? I don't know if I can do that from the front, John. This one says lights. So some of the photos might not come up. Can we dim the lights a little bit? Yeah, thanks. No, that's perfect. Perfect for me anyway, and for the sleepers. So this is a lovely photograph from Dave Cook from Cerro Casale, which is a gold-copper porphyry system in the high Andes. So we're about 5,100 meters. On the lithocaps, this is advanced argillic alteration right at the top of the system. Looking down towards the Cerro Casale porphyry center down below, it's about 1 kilometer further down, with all the alteration associated with it. So it's just illustrating, I guess, the scale of these systems. They're giant hydrothermal systems. They have a huge vertical extent, and also, as I'll show, a very large lateral extent as well. And that point is also emphasized by this photograph. So the open pit Chuquicamata in Chile. These deposits are huge things, giant geochemical anomalies, and arguably the most extreme geochemical anomalies that exist in the Earth's crust, or certainly some of them, these porphyry systems. So that's the scale, because you can't really tell what the scale is. So that's the pit at Chuqui. About 3 cubic kilometers of ore, mineralized material, 9 billion tons of rock. containing around 65 million tonnes of copper and a conservative estimate at least 110 million tonnes of sulfur. So although they're obviously metal resources, they have huge amounts of sulfur in them as well. And that's one of the key points I think we tend not to think about so much is the origin of sulfur and how it gets concentrated into these systems. But giant geochemical anomalies, that's what they are. Some of the just real basic stuff, porphyry deposits. So they're large tonnage deposits, and they started to be mined more than 100 years ago when the open pit method started to be developed that allowed these large low-grade resources to be extracted, principally for copper, molybdenum, and gold. Hypergene grades, so the initial mineralization, maybe sort of economic levels about 0.5, 0.6% copper, but certainly in some areas that you have this supergene enrichment via weathering that can increase the grade up to 1.5% or more, which is really important for some of the porphyry systems, particularly in the Andes, where you have this shallow, enriched zone near surface that's easily extracted, that can repay some of the capital costs early in the life of the project. Most mineralization is hosted in vein stockworks, and in cases such as the Los Bronces district, one of the greatest mineralized porphyry provinces, a lot of the mineralization is actually in magmatic hydrothermal breccias, a certain amount disseminated into into the host rocks as well, but primarily occurring in stockworks and breccias. But huge volumes of hydrothermal alteration associated with the mineralization, so a very large volume of rock being influenced. And systems formed from magmatic hydrothermal fluids, so exolving from a magma, passing through fractures in the rock, precipitating sulfide minerals, but importantly always associated with channeled through, partly being exolved from porphyritic intrusions and placed to relatively shallow crustal depths, mostly less than 5 kilometres, some even potentially as shallow as about 500 metres from surface. So they're shallow magmatic phenomena, or magmatic hydrothermal phenomena. And the photo just shows you an example of one of the porphyry fingers, one of the quartz monzonite porphyry fingers in the E27 copper gold deposit from North Park system in New South Wales. And this is very narrow porphyry finger. It's a cylindrical body around which the mineralization is zoned, just a couple hundred meters across. So, geodynamic settings, location, principally in oceanic continental arcs, so typical sort of cartoon that we might envisage the environment in which these are forming. Key steps: volatile transfer from the wedge, from the slab, melting the mantle wedge, mantles moving up into the lower crust, evolving in this region, migrating to shallower levels, either forming magma chambers or more increasingly considered sort of sill mush type zones in the middle crust, from which porphyritic magmas and fluids associated fluids are extracted with mineralization in the shallow part. So that's, in a nutshell, the model that we're talking about, the environment we're dealing with for the majority of porphyry systems. But we shouldn't forget that we also have porphyry deposits forming in other geodynamic environments post-collisional. We've got thickening of the lithosphere, melting potentially of the subcontinental lithospheric mantle or cumulate zone, enriched cumulate zone at the base of the crust. Delamination processes are also potentially allowing melting of the lower part of the lithosphere, or formation and extension, post-collisional extension, with a stenospheric upwelling and heating, and again, melting of the base of the lithosphere or into the crust as well, to produce the same sort of magmas that can form porphyry deposits. So any model that we have to explain how these deposits form has to be able to work in these different types of environments. You don't have to have active subduction going on to form a viable porphyry deposit. But they do have different characteristics, certain different characteristics, depending on which of these environments they're forming in. We can classify deposits by metal tenor, so this is the copper, gold, moly plot, just showing where the different deposits sit. So we've got this general trend along the bottom axis, so a lot of systems copper and moly with very limited gold. Associated generally as we head off in this direction towards molybdenum with increasing silica content of the associated magmas, and generally associated with continental arc settings. Whereas going up on this axis, as we're heading towards more gold-enriched systems, they tend to be in iron arc settings or post-subduction settings. And relatively few systems that sit in the middle, and we don't really fully understand why you have some of those deposits that both have copper, gold, and molybdenum in them. So there's a sort of some broad geodynamic controls on the metal tenor and the abundance of the different metals in the different porphyry systems. Now, I borrowed this from Bob Laux, he's in the room, which I wasn't sure if he would be or not, so apologies, Bob, if I misrepresent you on anything I might say at this point. But I'm just going to make a couple of points on the origin of sort of the gold enrichment in porphyry systems, and this was something that Bob considered with this spider diagram, and the data in the red symbols are effectively from gold-enriched porphyry environments, from magmas associated with gold-enriched porphyry environments, specifically the more primitive basaltic end members in those magmatic suites, compared with other systems that are less gold-enriched. And his point was that, particularly in terms of the high field strength elements, they're significantly enriched in those gold-fertile terrains, and interpreted that in terms of derivation of that source magma, either from an undepleted or a refertilized mantle source terrain. And possibly that was related to the melting of a previously metasomatized subcontinental lithospheric mantle. So that's one way of explaining why you get gold-enriched systems, and that's consistent with the geodynamic settings of things like post-subduction extension, which tend to be gold-enriched systems as well, where this type of process may well be taking place. Jeremy Richards sort of presented a sort of slightly alternative possibility explanation for the gold-copper endowment of porphyry systems, using this diagram modified from Campbell and Noldrip, which is the R value, the mass of silicate melt relative to the mass of sulfide in the system, and plotting on this axis the gold content of the melt in terms of in the yellow lines and the copper content in the green lines. And the point of this diagram is to show that in this sort of intermediate range where R values sort of exceed about 1,000, that's where you generate the sort of maximum copper extraction from melting the source. Whereas to generate the maximum gold enrichment, you can do that at higher R values where you've got effectively a smaller amount of residual sulfide in the source. So he's pointing out that because of the different partitioning behavior of copper and gold between sulfide and silicate melt, you can effectively fractionate the two metals depending on how much sulfide you have in your source. So there's different ways of generating the variation in those metal ratios. If we look back into the geological record of porphyry deposit formation, there are some obvious temporal patterns. The most obvious one being that the predominance of deposits are in the Cenozoic and a calc-alkaline affinity. That's not really that surprising, given that these systems are placed into the shallow crust and for a large part in active continental margin environments where they're likely to be destroyed by exhumation and erosion. So that's the main reason, presumably, why we don't see too many in the rock record, further back in the rock record. The second point is there a higher proportion of island arc systems and collision zone systems in the recent past, and that may be because they tend to be placed at shallower depth, and perhaps they've also got possibly greater exhumation potential. So we're seeing them exposed even though they're younger at the Earth's surface where they can be discovered. And a sort of corollary of that is that the calc-alkaline systems, which presumably are forming at the present day, are there, but they just haven't been. They're environments which tend not to be exhumed so quickly, so they tend not to be exhumed so easily. You maybe need some slightly more special geodynamic environments to exhume a very young, typical calc-alkaline continental margin porphyry system. To get a feel for what the shallow crustal part of the porphyry system looks like, it's a good idea to go to Yerington in Nevada, and this is the map view produced from the work of John Dillis and his colleagues over a number of years. And it's really nice because of basin range extension, the whole system's been tilted on its side, so the map is effectively a cross-section of the Earth's crust. And you can see the Lure Hill granite, equigranular granitic, sort of batholithic body down at the bottom, with its dikes and porphyry fingers feeding up into the overlying rocks and up towards the inferred paleo surface at the time. And here the two porphyry centres, the Van Mason and MacArthur, shown with various alteration types shown on the map as well. So it gives you quite a good sense of what the cross-section through a porphyry system, at least the shallow part of it, looks like. And we just overlay the sort of typical cartoon, one of the typical cartoon models of the porphyry ore forming process on this scale alongside this. So you can envisage the draining of fluids from this mush reservoir down in here, up through the porphyry fingers that are being placed up into the carapace of this larger magmatic system, carrying metals in solution and precipitating them into the ore zone with the associated alteration zones around the outside. Put together this sort of roll call of causative porphyries. Just to give you a sort of a bit of a feel for the textures you get in these rocks. So some of the big ones at this end, from some of the biggest porphyry deposits on the planet. So we've got El Teniente in here, the dacite porphyry, which is the last but most volumetrically large intrusion that's temporarily overlapping the mineralization. Quartz monzonite from Rio Blanco, Los Bronces district. Quartz latite from Resolution, latite porphyry from Bingham, quartz diorite, Cerro it's a relatively small system in Peru. Quartz monzonite from Oyotogo and quartz monzonite from North Parks. And although there is a sort of a slight distinction between copper moly systems, which tend to be a bit more towards the felsic end, and the copper gold systems, which tend to be associated with slightly more primitive magmas, there's a huge porphyry stage magmas anyway, there's a huge overlap. So there's not too much difference in many ways in the compositions. A lot of these are monzonites, monzonitic type compositions are associated with most closely associated with the mineralizing events. And there's a huge degree of variation in textures within any one of these kind of intrusive units, from crowded to uncrowded porphyries, variations in the abundance of the different mineral phases. But they do all have a porphyritic texture, so obviously that's relevant probably to something to do with the process that we're dealing with. The change in colour here is mainly because at least these slightly more reddened ones at the end is related to the alteration. So although these were sampled as to be as fresh as possible examples of those lithologies, there's still some alteration, and you particularly get this characteristic hematitic dusting that's much more characteristic in the copper gold, alkalic, particularly the alkalic copper gold systems. It's given them a bit of that reddening colour. So let's talk a little bit more about the alteration footprint. So this is the cartoon of our porphyry centre, potassic zone in the core grading outwards into the surrounding propylitic halo, which I'll talk more about towards the end, the green rock environment as we call it. And then upwards we have a transition into phyllic, so sericitic, quartz, muscovite, pyrite alteration, which may sort of overprint downwards onto the core of the system, then grading upwards into argillic, and our advanced argillic cap over the top, so-called lithocap environment. So that's the sort of typical alteration distribution. Obviously varies hugely from system to system depending on structural controls and so on. But that's the typical sort of characteristics that we see. So I'll show you some photos now of the different alteration types, just some nice photographs of potassic alteration first. So some vein systems in North Parks, K-feldspar halos, intense orthoclase flooding, again from North Parks, it's the E26 North deposit, associated with the stockwork. Magnetite quartz veins, typically associated with potassic zone as well from Ridgeway. And this is an example from El Teniente, one of the early vein generations from Vicky Vrye's work. And this is actually an anhydrite quartz biotite chlorite vein with plagioclase halos. So a little bit unusual having plagioclase halos, but we see that quite a lot in the early high temperature potassic veins at El Teniente, where in the mafic host rocks we tend to get biotite as the stable potassic phase, as opposed to in the more felsic host rocks where we get the K-feldspar. So that's potassic alteration. Let's move outwards laterally into the propylitic alteration. Green rocks, predominantly characterized by the presence of calcite, epidote, chlorite, sometimes hematite, albite, zeolites out in the real distal parts of the system as well. And phyllic alteration. The phyllic alteration can form huge volumes of alteration. So this is an example from the Agua Amarga, just the west of El Teniente, where the whole mountainside has been altered in a phyllic alteration style with also argillic alteration in there as well. So huge volumes of rock being altered by fluids escaping from these systems. And lastly, just some examples of advanced argillic alteration, which in an extreme case you end up with this vuggy silica rock where everything's been leached away basically by highly acidic fluids with just this residual quartz left behind. Okay, I'm not going to say very much about hypergene mineralization. They're the main ore minerals, tend to get zonation of the sulfides, some late stage veins with base metal sulfides being introduced. And a cartoon cross-section showing an example, again, from one of these porphyry fingers, shown in yellow, from North Park District again, with this tight zonation of copper grades around that porphyry finger and the gold concentrated down in the core, down in here. Okay, so that's hopefully everyone's on the same page. Everyone knows what a porphyry deposit is. This has some idea of the sort of alteration that surrounds them. So let's talk a little bit about the ore forming process. This would be kind of like the conventional wisdom. I guess a lot of people in the economic geology community would still believe this is a general model for how porphyry deposits form in the ore forming environment itself, at the level of the sort of deposition of the sulfides, if you like, where the most likely fluid to be exsolving from the magmatic system is a single phase fluid, and as it cools and decompresses, undergoes phase separation to produce coexisting vapor and brine phases, as represented by the fluid inclusions in here. As a result of cooling, we get disproportionation of SO2 in that fluid, which produces H2S and acidity, and that results in the precipitation of metals. There's a range of controls of precipitation of sulfides, which will vary depending on which system you're in, which is more important, but probably quite a few different processes can play a role in pushing sulfides towards saturation point. So in detail, it's complicated, but the general model, I think, is fairly clear. And these are just a couple of examples where, from fluid inclusion data, suggestion here that we've got a decrease in copper content over the temperature window of around 450 to about 350, where there's a big decrease in chalcopyrite solubility from experimental data. So this can be decrease in copper in the fluid, just literally caused by cooling of the fluids as they're migrating upwards into the overlying cooler rocks. And this is some experimental data from Gleb Pokrovsky's group showing that the solubility, at least in the vapor phase, is related to the density of that fluid. So if you have a vapor phase that's separated off during phase separation, that's migrating upwards, and if it's under conditions where it can undergo an expansion and the density is decreasing, then the solubility of basically everything as a chloride complex will decrease as a result of decreasing fluid density. So that will be something that will be driving sulfides towards saturation as well. But the message really is one fluid is all it takes. This has been very nicely illustrated by Mark Reed from his reactive transport modeling based on the Butte system in Montana. And he showed that a single magmatic hydrothermal fluid, intermediate density type fluid of lowish to moderate salinity, can reproduce all the observed mineral assemblages that we get in porphyry systems, including the ore mineral assemblages, by cooling and reaction with the host rocks. And this diagram is a really nice illustration of the modeling results, diagram of temperature against the effective water-rock ratio, so how much the fluid has interacted and equilibrated with the surrounding host rocks. And plotted on this as a sort of effectively the product of all their modelling runs to show where different minerals are stabilised as a function of temperature and water-rock ratio. And there's various paths shown on here, but to simplify it, just put that over the top so you can see where basically these different fields for the main alteration assemblages would sit. So we can explain the transition outward from potassic stable assemblages into the propylitic regime by a path that comes over the top, where a fluid is generally at becoming relatively strongly equilibrated with the rock, so it's approaching lower fluid rock ratios at moderate and then increasingly lower temperatures as it's migrating outwards. You can explain the transition from potassic to propylitic assemblages. Where you have structural controls and the fluids are getting more focused, you have higher fluid rock ratios. Effectively, you generate lower pH conditions where you can shift from plagioclase stability, feldspar stability, into the muscovite stability field. Plagioclase starts to break down and you produce the phyllic assemblages. And then in extreme bottom high fluid rock ratios where maybe the fluids are going straight up through the spout, up the top of the system, where the most acidic conditions are developed, you get argillic, transitional to advanced argillic assemblages developed. So one fluid, depending on which path it takes, can produce any of those alteration assemblages. But sulfur is a key component, as I sort of alluded to earlier, that porphyry systems more than anything are sulfur anomalies. So what record is there of sulfur in these fluids? And there's very limited data, and this is a really important paper published by the ETH group, Seo et al., 2009, where they actually measured for the first time sulfur contents of fluid inclusions from a range of magmatic hydrothermal systems. And plotted on here is the stoichiometric molar ratio of copper to sulfur in chalcopyrite at 1 to 2. And all of these vapor fluid inclusions and all of these brine fluid inclusions sit on the sulfur excess side of that ratio. So they all have sufficient sulfur in to precipitate all of the copper that's present in the fluid, in theory. So there's not a sulfur limitation from precipitating all of the copper from a single fluid, either for brines or for vapors or for the precursor fluid that would have split into these brines and vapors. So there may not be a sulfur problem in the sense that there does appear to be quite a lot of sulfur present in these magmatic hydrothermal fluids. So that's the sort of end of the first introductory part. And now I'll sort of go into talk a little bit about some of the things that we're doing and other people are doing and how we assess the potential fertility of magmatic suites of rocks for porphyrogenesis. So can we look at something in a rock, whole rock data or mineral chemistry data from a rock from a certain belt, some arc segment somewhere around the world, and get some idea, is there some signature in that rock that that system was capable of producing a porphyry deposit? So although there's probably a convergence of opinion on the ore forming processes at the ore deposit level, it's unclear what makes some systems fertile. The relative endowment of different arcs with respect to copper is nicely illustrated in this slide from Epidote, 2012. The porphyry systems, this is showing all copper basically, but the porphyry systems are shown in red, so just concentrate on those. And it shows that not all arcs are born equal. So if you look at the Chilean Andes, northern Chile, and the central Miocene-Pliocene belt, there's 2 orders of magnitude more copper endowment in these 2 arc segments than in, say, Japan. So there's huge variations depending on where you are, what type of arc segment you're in. And we don't fully understand those differences. But it's obviously critical for exploration to understand if you were at a fairly early stage of assessment of a particular arc terrain. It's pretty critical to be able to understand what the difference is between those environments, why one is so much more fertile, so much better endowed than the other. And one of the key approaches that's been developed from a whole rock point of view, also by Bob, over the past probably 10 or 15 years, I guess, is a whole rock approach, and there's a range of parameters that Bob's developed based on whole rock data to try and separate igneous rocks associated with fertile systems from sort of barren reference suites. And that's what it's shown on this diagram, strontium-yttrium ratio being one of the most popular ratios, plotted as a function of the silica content. And all of the symbols in pink and red are all fertile porphyry environments, and they all diverge from this trend along the bottom, which is from this unproductive reference suite data set. So the normal arc, magma trends off, gradually decreasing strontium-yttrium ratio with evolution, differentiation, increasing silica, whereas from about 68% approximately, all of these porphyry-related magmatic rocks go up, increasing significantly in strontium-yttrium ratio. And that's been interpreted in terms of 2 processes: increasing strontium by suppression of plagioclase crystallization as a result of high H2O in the melt, combined with depletion of yttrium as a result of amphibole fractionation, also related to the water content of the melt. So high content water in the melt, something we probably need to form significant magmatic hydrothermal systems from in porphyries. So we probably need high magmatic water, and that characteristic driving this strontium-yttrium ratio to high values. So it could be just tracing magmatic water content. But there is clearly a difference, a divergence in behavior from normal arc, going along here, from porphyry deposits. So they're kind of like representative of an abnormal arc process, or they're an end member or an extreme product of some unusual set of circumstances. But we're talking about whole rock. Strontium is very mobile, and that's illustrated in some diagrams here from a recent PhD student of mine, Jake Longridge, based on his work at Cerro Corona in Peru, who did a mass transfer analysis looking at the element mobility in different alteration zones in the Cerro Corona system with different sort of overprinting relationships. And what he showed was for strontium, so this is strontium change, parts per million, from an initial strontium of about 470 ppm in the rock, that potassic alteration in general removes strontium from the rock. Propylitic alteration removes strontium from the rock, so about half of it's removed in this potassic alteration domain. If you overprint propylitic on top of a pre-existing potassic, you remove up to almost the other half. So by the time you've had propylitic and potassic, you've removed a large proportion of the strontium from the rock. That's in the inner propylitic zone. It's actually redistributed the strontium further out, and I'll show you that in the mineral chemistry towards the end. Philic alteration also tends to remove strontium, as does argillic alteration. So all of these alteration domains are stripping strontium from the whole rock and mobilizing it. Exception being this Dicite alteration, which you see at Cerro Corona, which is, I think is probably related to a later epithermal overprint, so it's doing something a bit different. So strontium is mobile, so you have to be really careful using a whole rock approach to be able to filter out all of the weak alteration and other factors that can result in contaminating effectively that fertility signal. You might get a false negative in sense of any of these samples are giving you a lower strontium than you should have. Even relatively weak alteration, I mean, some of this propylitic alteration is not particularly strong in terms of other parameters, other rock characteristics, but in terms of strontium, there's significant removal. So you have to be quite careful applying those whole rock approaches. So, can we go to some mineral archives that may be more robust? And zircon's been a very popular one. There's been a lot of work being done on it over the past few years, and still a lot of interest in zircon geochemistry, in magmatic systems in general, but particularly in terms of how you could apply zircon chemistry in understanding porphyry systems. There's a couple of figures from Matt Loder's paper in 2000, that came out this year, in 2007 in EPSL, which he'll talk more about in his presentation. So I don't want to say too much, but the point is, as has been noted a number of times in the literature, that the europium and cerium anomalies in zircon can discriminate to some extent fertile porphyry systems in black from barren reference suites shown in grey. Obviously, there's a fair bit of overlap, but you can see general elevated cerium anomaly and europium anomaly in the fertile, zircons from fertile systems. And probably tracking magma FO2, certainly in terms of the cerium star, potentially that also for europium star, and indirectly also the water content of the melt. So tracking important processes, FO2, we think magma is associated with porphyry systems. To form porphyry deposits have to be relatively oxidized and relatively water-rich. But these signatures can be compromised by things like co-crystallization of titanite. So it's the model that Matt put together to show the europium anomaly for a set of data from Oyo Tolgoi. Variations in the europium anomaly and increases that we see in europium anomaly in these particularly low tantalum zircons in the black dots can be explained by crystallization, co-crystallization or earlier crystallization of really small amounts of titanite. And that can also affect some of the geochemistry of the zircons as well in terms of the middle heavy rare earth ratio. So we have to be careful that we're not getting a signal that's actually being produced by something that's not related necessarily to the fertility but something else. So that's work in progress. And another example is plagioclase. Matt Hodgkinson in the audience is going to be talking about this later in the conference as well. So this was developed by Ben Williamson et al. In 2016, where they showed that the aluminium content of plagioclase feldspar from fertile porphyry systems is elevated relative to sort of barren reference data sets. And in terms of whole rocks, that sort of enrichment of aluminium in fertile systems has been known about for a long time. Here's another plot from one of Bob's papers, showing again in the red symbols the fertile systems tending to have a higher aluminium titanium oxide ratio than the barren reference suites. So elevation of aluminium, whether it's in plagioclase or in whole rock, is a characteristic of more fertile systems. And there are lots of other minerals we could look at as well, and that we are working on. So as an example from Rob Siverite's work on magnetite. This is from the Schultz granite, which is thought to be the parental sort of plutonic intrusion associated with systems in Arizona, particularly Resolution porphyry deposit. Apatite, this is an example from Emily Bruges' work. He's working with us on apatite from Chuquicamata, recently presented on that at the SGA conference a couple of weeks ago. And some amphiboles that I've stolen from Dan Smith. Sorry, Dan, I forgot to ask you whether I could show this photo, but I have anyway. So we actually analysed some of these high aluminium amphiboles for the grant application for the NERC famous project that I'm about to say a little bit more about. So there's lots of other mineral archives in there that we can interrogate, crystallise at different stages of evolution of these rocks to try and understand more about the processes that are, key to the formation of porphyry deposits, what makes porphyry magmas evolve along a different path from typical arc magmas. And a lot of these things are going to be things that are going to be discussed in talks over the coming couple of days. So looking at these archives, these mineral records, is a key part of the NERC famous project. which has just got underway, and that's one of the reasons I was asked to talk here, to say something briefly about this project. So it's a large NERC funded project. It's a highlight topic, which is kind of like ideas submitted by the earth science community in the UK, and then NERC consider them and then release a call for specific topics. And there was one on this kind of area of research, if you like, magmatic fertility. The goal of the project is going to endeavour to address the fundamental scientific processes that lead to the formation of porphyry ore deposits, but at the same time develop mineral proxies that potentially could be used in exploration. So developing, identifying fingerprints or indicators in minerals that a company could go out and measure to give them some idea of the processes that we need to form porphyry deposits have happened in a particular area, whether that's on the arc segment scale, whether that's on district scale and individual intrusion scale. They may be different signals, but there are potentially signals there that can allow us to distinguish whether a system was capable of forming a deposit. It doesn't tell us that it did or not. That's then the job of the exploration company to find where it might be located, but whether that system was capable of forming something. So the project's got 8 collaborating institutions in the UK, a number of companies supporting us, providing access to data and field sampling sites, consultants, Dixilito's involved, and some companies are interested in sort of downstream technology, so when we're able to develop some tools that might be useful for exploration, how they can actually be developed, acquisition of the data that's required, how that can be streamlined, made cheaper, whatever. So the companies involved interested in those aspects, the downstream aspects as well. And a range of sort of key international partners involved as well. So it's a sort of truly international endeavour, and it needs to be because it's a big problem. And it'd be great if more of the people involved in the room who are not somehow on this list would be interested in collaborating with us as well on a famous project, because it's really what we need to do. The sort of concept of the grant and the way it was put together was around this concept of a series of gates. So these are not exclusive, but they're the ones we sort of kind of focused on. And when I say gate, it's sort of a gate that the magma had to go through, or maybe had to avoid going through, during its evolution to become what we call fertile. This is the sort of path of fertility, loosely from the bottom towards the top. And there are 5 gates that may be occurring maybe more than once during this sort of sequence. But they're the sort of areas of focus, if you like, of the science. We're trying to look at these particular processes, how important they are, what the signatures are of these processes are in the arc magma system, and how critical they are for porphyry ore formation. 2 goals, main goals: develop new process models for porphyry deposits, hopefully some maybe new ideas of how porphyry deposits form, and also develop tools, so develop something that's useful for exploration. Part 3, so now we're going into the exploration targeting space. This photo is an example from the Endeavour porphyry copper system in New South Wales, which before it was discovered was just happily sitting here beneath these rolling hills and this farmland, unknown, and it was only discovered because of some regional sampling that was done by a company alongside one of the roads that was running through the middle here, and they found geochemical anomalies and suggested there might be something interesting, so then they did grid drilling. So buried systems under cover is what this research has been sort of focused towards, really, in many ways, because most of the significant deposits at surface will have been discovered on Earth. And so companies, especially the big ones, are increasingly looking under deeper and deeper cover. So how do we look under deeper cover? How do we assess where the centre of a system is? If we can't see it exposed at surface, how can we assess whether it's significantly mineralised or not? Those are the sorts of questions we're trying to tackle. And I can illustrate it with this, going back to this Alteration cartoon. There's a little animation that Paul Agnew, Rio Tinto, put together to illustrate the problem from an industry perspective, if you like. So that was the Alteration cartoon, and now we've just sort of emphasised the green rock, the proprolitic environment. So extending out, we now know a long distance away from the centre of these systems too, and in the bigger deposits up to maybe 6 kilometres away from the deposit centre. So a huge volume of altered rock, significantly enlarging the footprint for exploration, if we can understand it. If we can explore within this, we've got a much larger target, which might be telling us that there's something down here. But we've eroded it, and we look at it in 3D, put the terrain back on, and then we've covered up the surface with post-mineral gravels. So all we have is this little strip of propylitic altered rock in this range front. That's all we have to work with. So from taking samples in this propylitically altered rock over here, can we say something about whether there's a porphyry centre over there buried under the gravel, where it is, and whether it might be mineralised or not. So that's what we're trying to do. And that distance may be, several kilometres. So they're the questions I kind of, I guess I've alluded to them already. Can we vector towards the centre of the system? Can we assess the endowment? And also, can we use lithocap mineralogy and chemistry in the same sort of ways where we have lithocap preserved? And ultimately, can we reduce the cost, time, and environmental impact of making a discovery? So these are some examples of epidote chemistry. So I'll just take you through these three panels here. The top left one is from the Baguio district in the Philippines, work published by Dave Cook and colleagues. And it's kind of like a transector samples, which goes through three systems: the Skarn system over here, Mexico Skarn, the Black Mountain small porphyry system here, and Nugget Hill, which is probably quite a large porphyry system, but it sits under the Philippine Military Academy, so will never be mined, but is probably pretty juicy by all accounts from our mineral chemistry anyway. So this is the epidote chemistry shown in the blue triangles, and what this is trying to show is that there's a sort of a significant increase in the lead content of the epidote as we move away from the Nugget Hill porphyry, and then it drops off again down towards the Black Mountain porphyry, so kind of like a maximum in the middle. And that's a pattern we see repeated in a number of systems we've looked at, where you tend to get this increase in lead content of epidote as you move out away from the system. The red dots are whole rock data, so they do show significant lead anomalism on the edge of this yellow band, which is the pyrite halo surrounding Nugget Hill porphyry. But as soon as you get beyond the pyrite halo, that lead anomalism in whole rock drops off, but that's where the epidote kicks up. So the point is really the epidote's giving you a much broader footprint to the system than you can see from whole rock geochemistry. The bottom one is an example of epidote from Taudi Balak in Kyrgyzstan, copper-gold system. And the data are gridded up here, contoured, because it was a fairly evenly distributed sampling. And you can see there's this low in arsenic that sits right over the top of the ore body. And that, again, that's something we see consistently. Arsenic in epidote is low, proximal in the centre of the system. And here's another example from El Teniente. This sort of butterfly-shaped low, which is the low in arsenic. And that's where the ore shell sits in the El Teniente system. And probably our sampling didn't really go out far enough to really pick up the arsenic high. So the arsenic maximum in epidote is really a long way away from the El Teniente centre, 4, 5, maybe even 6 kilometres away. So we haven't properly defined that outer halo where arsenic starts to increase in the epidote. So arsenic happily goes into the epidote structure, we know that. So it's quite a useful indicator of the distal fringes of a propylitic halo, if you like, and then the gradient of decreasing concentrations as you head in towards the centre. Antimony shows something a little bit sort of similar, but there's a little bit of a sort of small high in the middle and then the kind of low surrounding it. Some of the rare earth elements like terbium shows a low in the centre but kind of like high, kind of on the shoulder of the deposit almost. Some of these things have sort of gridding artefacts due to the probably not quite enough samples. And copper tends to be high proximal here. It just sits on the edge of the ore zone in the bottom southeast corner. But copper tends to be elevated in epidote. When you're close to the system centre, whether that's actually truly in the lattice, we don't really know. It may well be that it's actually present as nano inclusions of sulfides. But it is often enriched when you get close. Couple of illustrations of chlorite. So first, the chlorite geothermometry. So chlorite, you can use various calibrations related to the aluminium, tetrahedral aluminium content of chlorite, to calculate crystallization temperature, and these are data from the Bata-Hijau system showing decrease in temperature, loosely exponential as we move away from the centre, and that's the same data sort of contoured up in map view. That's the Bata-Hijau centre, and it shows quite nicely. You've got a nice thermal anomaly associated with the porphyry system, fairly steep drop off on both sides to north and south, and then this ridge of kind of higher temperature trending off towards this other prospect of Sekonkang up in the west-northwest. We think that's actually mapping out the underlying igneous, sort of more plutonic igneous system that's underlying the Bata-Hijau area. So chlorite temperature is good for mapping out the thermal structure, if you like, of the porphyry environment on a sort of few tens of kilometre kind of scale. And that's another little image from El Teniente just showing chlorite thermometry. The star shows the center of the ore body. So the thermal anomaly is really well defined from the chlorite chemistry at El Teniente as well. And that just shows the sort of alteration facies in map view, that trend across the west-northwest with higher intensity of propylitic alteration. That's actinolite bearing in blue, some intrusive centers in pink. So it's just illustrating that higher temperature ridge, if you like, that the chlorite chemistry is mapping out. So looking at some of the trace elements in chlorite, there's a whole range of different things that appear to substitute in chlorite structure. Lithium shows a proximal low, that's El Teniente again. Arsenic, like Epidote, is low in the center. Strontium shows a low in the center. Cobalt maybe is showing a bit more of a shoulder, so it's a sort of kind of low in the center with a ridge around the outside. This is another example from the Tau Black system. And here we've got this ratio of titanium to strontium that really emphasizes the anomaly in chlorite chemistry over the ore zone. And that's based on the fact that titanium this is from the Badajoz data set, titanium is high in chlorite when you're close to the center of the system and drops off out to about 2.5 kilometers away from Badajoz. So the titanium is tracking, we think, the temperature primarily. And extends, that gradient extends well beyond the pyrite, observable pyrite halo. So it gives us an indication of the direction towards the center from much further out than you can tell from observations of the rock or the whole rock geochemistry anomalism. And then it seems to go off into some sort of noisy background. You lose any clearly defined gradient. But if you've got things that are enriched proximal, like titanium, and depleted, like strontium, then you can generate a ratio that enhances the signal to noise, if you like, or the anomaly to background, which is what's been done here, and strongly showing there's a big titanium-strontium anomaly associated with the deposit at Tau Black. So just looking at these data a little bit more detail briefly at Badajoz. So this is sampling traverses that went off towards the north, south, and southwest, showing this steep drop in titanium-strontium ratio now. The blue symbols are samples along that traverse across the west, so that's where we're tracking that elevated temperature ridge. So we're seeing a less significant decrease in that ratio, which is reflecting the fact that titanium's not dropping off as steeply. But for traverses in most of the directions, this gradient is fairly consistent, and we can fit a simple exponential to that, which gives us a prediction, if you like, of the distance that we are away from the center. In the Badajoz case, for sort of 3/4 of the way around the deposit at least, that's a very accurate prediction of the distance of any sample point to the center. So although it's dangerous to start applying that anywhere, because obviously the gradients we're talking about will vary from place to place, it gives us a sense that we can start to develop methods for predicting the distance, not just the direction towards the center of something, but potentially how far away we might be. And this is the sort of thing that companies are now developing in-house using their own technology to improve on this. So at the risk of labouring the point, chlorite chemistry gradients are proving to be extremely useful for targeting the centre of porphyry systems, and this is a titanium-lithium ratio, El Teniente. Just picking out that highlights a satellite system that's a known mineralised satellite to El Teniente called La Huifa, just to the northeast. And that's the 0.58% copper grade shell El Teniente, perfectly mapped out by the titanium-lithium ratio in chlorite. So what controls these gradients? Well, we haven't, it's early days really, we haven't done too much work on this. We know tetrahedral aluminium chlorite is temperature controlled. We're pretty confident that titanium is also, as it is in biotite. Strontium, as I've shown, is mobile in wholerock in a propylitic domain, and we think is being flushed outwards into the outer propylitic environment. So it's depleted in the core in wholerock, it's depleted in the core in chlorite, and in other minerals as well, and is increasing out towards the fringes of the propylitic system. Probably a function of pH and temperature, strontium mobility in fluid, but also its partitioning between coexisting phases that are also precipitating within the propylitic halo, like calcite and epidote, which also provide a home for strontium. So there's a range of controls that's probably quite complicated in detail, and we need to do some more investigation to understand that better. So just coming towards the end, I knew I'd run out of time, so I haven't got anything prepared on lithocaps apart from this one slide, just to show you a really beautiful lithocap. This is a Shatin in Mongolia. So this is the advanced orogenic alteration cap that may, in this case, sit above porphyry system at depth. And there have been companies in the past that have drilled this, not many drill holes into it, and there are companies at the moment exploring it, so it's still a potential target. There may be something underneath, but how do we know where underneath the porphyry centre might be? This whole thing might have been generated by one large porphyry deposit. This end might be over here because this bit of it might have been eroded away. So how do we know where that centre is, and how do we know, even if there is a centre there, whether it's significantly mineralised? So again, the same sort of questions. And the sort of things that are being done in lithocap space, looking particularly at whole rock and also alunite chemistry, variations, systematic variations in lithocap environments. This is the Lepanto far southeast system in the Philippines, and shows some variations in a range of chemical parameters. And some of these can also be mapped using shortwave infrared spectroscopy as well, which are reflecting variations in sodium-potassium substitution into the alunite structure in this case. So it's a way of using a spectroscopic technique to map out chemical variations in the mineral. So, just some final thoughts to wrap it up. I think it's enough data for whole rock geochemistry and for the mineral chemistry. We know that porphyry deposits are recorded as atypical arc magma evolution, so they represent some divergent path of magma evolution that's not normal for arcs. I'd argue the order depositional controls in a general sense are fairly well understood. That's not perhaps surprising given that there's been 100 years or more of research on porphyry ore deposits themselves and all of the things that go on, but not very much relatively in the much deeper mineral system of which the porphyry deposit is the end product. But controls on spatial and temporal localization of fertile arc segments are not well understood, and that's obviously where the focus of the famous research project is, to try and much better understand why certain domains are much more prospective for forming porphyry systems, why certain segments or certain time periods of certain arc segments, the magmas are allowed to go through the gates and generate potential for ore formation. And lastly, I've given some examples. Mineral chemistry is providing key new tools that industry are using in exploration. And it's important in this age of demonstrating impact of our research that we can show that we're doing things which industry can take on board and use. And that is the case for some of these mineral chemistry tools. The major companies are using them in their active exploration day to day right now. And what we need is a discovery company to find something where they're actually happy to come out and say, we used these methods and they really helped us in this discovery. And then we'll be happy. So I'll leave it there. I'm happy to take any questions over a beer because I have run over time. Thanks very much. Oh, and I forgot to say that this is courtesy of Matt Loader. It's his favourite address in the world. I'm sure in Superior, Arizona. I'm sure he'd like to buy a house and live here one day. Magma Ave and Porphyry Street. So thanks, Matt.
Thank you very much, Jamie. That's an
Okay.
excellent talk. We've got time for a couple of questions before beers. I mean, the beers are waiting for us outside. Are there any questions from the floor? John?
Jeremy, if the main process is cooling to precipitate the minerals, the sulfides, I would imagine the distribution would map out the relevant isotherm.
Yeah. So I mean, I guess it's the ETH group that's led a lot on making the case for cooling, and I think there is a case for cooling. We know the fluids are going to go through steep thermal gradients, and the models that they've done do predict the generation of the copper grade shell where the fluid in their model is going through the steep temperature drop across that critical window, about 450, 500, 450 to about 350 or 300. So where the fluids go through that in their models, they can generate the same form of the copper grade shell, typically an inverted cup shape, because the fluids are kind of like coming up and they're also like sort of diverging. So generate this, effectively it is mapping the copper grade shell. This cup is mapping out the isotherm of around about 400 or 350. So it sort of works. I mean, I don't think cooling is the only process, but we know it's going to happen. We know it's going to be pretty strong gradient in that kind of environment. And certainly there's a very strong temperature dependence of chalcopyrite solubility in that temperature range. So almost certainly is playing a role, but it's not going to be the only thing. Because we know there are differences between porphyry systems in different host rocks where reduced iron or the oxidation state of the host rock may be influencing how effective the trap it is. So there's other factors at play as well. Certainly host rocks can play a role.
My feeling is though that ore shells normally have a bottom.
No, they don't. So
They
Bingham's
keep on going, though.
yeah, well, Bingham's a brilliant example where the grade shell is like it's always described as a molar tooth, where it has a big cap over the top and it goes down into these sort of tooth-like projections, almost like prongs, that eventually, I mean, the grade continues to quite significant depths, but then eventually they sort of pinch out. So if you imagine it like a molar tooth shape, effectively. So it's mainly at the top and then down the sides.
I can't imagine a process that produces a molar tooth-shaped isotope.
Yeah, I mean, I think the top part of the tooth, they can explain in their model. Whether they can explain the very deep parts is another question. Yeah. Broadly, loosely, it's isotherm shaped.
I've just got a short one. To what extent does stream sediment and soil sampling carried out routinely by National Geological Surveys, for example, provide you with all the information you require, or do you need to make special additions to that?
It can potentially provide us with the material that we require. So we haven't done much going out into stream sediment sampling world, but that's something that's obviously up there, and it's something that Rio Tinto, for example, are doing. And we would potentially collaborate with them, maybe looking at some of those samples. What they have is they have samples that they can use effectively as a background. So magnetite, whatever it might be, Epidote in some stream sediment sample, draining a completely barren terrain, they can analyse the chemistry and then use that information as a baseline for comparison with known porphyry-related systems. And obviously it's something that we've been doing sampling in rocks and analysing the minerals in rocks to get these sort of fertility or vector signals out, but it's something you could obviously do on stream sediments as well and evaluate catchments. And there's some clear applications, particularly for something like magnetite, which is obviously so easy to separate, for doing that. So we haven't done much of it. I suspect some of the companies are doing that already. But yeah, we need those samples, and but we need the trace element chemistry of them. That's the key. Not just whole sample analysis. We need to analyse the minerals individually.
The focus was on active or modern arcs as a setting for these, but you mentioned briefly that there were also post-subduction examples. Do you have an idea of how significant the post-subduction examples might be in the rock record relative to the arcs?
Well, I mean, I guess it's probably fair to say there's something that's kind of been emerging over the last 10 or 20 years as something that's a significantly different environment for formation of porphyry deposits, and they're increasingly better understood. I mean, Massimo's much better placed probably to answer this question, as is Dan, various people who worked on these. So I haven't worked on post-subduction systems myself. As you may have gathered, I didn't really talk about them very much. But
Could you give us some examples? What do you call it? Give an example of post-subduction.
well, I think Bingham's a really good example. So there's no evidence of an active subduction zone anywhere near Bingham when it was forming. So one of the more recent models for Bingham is actually melting of previously metasomatized mantle from a subduction zone from the Proterozoic. So there was metasomatized mantle there, and in the basin and range extension in the Eocene, that was extended, and you had one of those, you've extended a stenospheric upwelling, and you're melting that previously metasomatized zone. So it has the same process, effectively, generating the source magma as you would have in an active subduction zone, but in a different geodynamic environment. So that's one example. I mean, Dan, perhaps throw in a few more.
Most of the stuff I've looked at has been more on the epithermal side of things rather than the porphyry, so I would have said Bingham as a textbook example of the post-subduction porphyry, but for the epithermal deposits, it includes some of the really world-class ones, so Cripple Creek, Porgera, Emperor in Fiji, they're all distinct in space and time from the active subduction in that region. They're all associated with extension.
That's what gold deposits.
Those are the gold deposits, the epithermal deposits. So for the porphyry deposits, Bingham will be the biggest, most significant. I think some of the more alkalic Canadian deposits.
There's a lot in the Tethyan belt as well. I mean, there's a lot in the Tethyan belt.
Yes.
So I just wanted to come back to along the tooth concept, because no, it's actually something that struck about. It's an analogy different depths as the intrusion comes up. I mean, I don't know if it's similar to Porphyry-type because I've never really worked on them, but it was just an idea because you get the sort of the sodium-rich fluids coming out at depth, and then as you come up and up and up, you get the potassic fluids, and you get these sorts of cone-shaped stringer structures of alteration coming out from a central intrusion. I don't know if that helps.
Yeah, that's interesting. Yeah, I mean, yeah, I don't completely understand that. I guess that form, and there's a lot of things that could be playing a role because there's variation in host rocks. There's obviously structures that have controlled the localization of emplacement of the intrusions themselves that may be producing permeability, heterogeneity that might be, and that's clearly the case at Bingham, that may be focusing fluids along pipe-like zones. Effectively, you've got structural intersections. You can just generate pipe-like zones of elevated permeability. I mean, it's not directly related, but Bingham's really interesting because it has a very deep extension of molybdenum zone. So molybdenum's generally fairly late at Bingham. It doesn't fit into the copper-gold story so easily. And it's also extensive to great depth. So there's some really deep holes under Bingham that Simon Kocher, one of my PhD students, was working on. And the molybdenum grade goes to sort of 2 kilometres below the existing deposit. It's a huge vertical extent, at least of molybdenum precipitation, molybdenite, and that's what's predominantly down there. So you're well below the copper zone, but you've got this very deep zone of molybdenite saturation and precipitation through a huge vertical extent. Ore grades down, 2 kilometres vertically. It's quite amazing.
Okay. Thanks very much again, Jamie.
Thank you.